Welcome to part 2 of ventilators. Here we'll review vent types, specifically pressure control versus volume control, and then we'll talk about the inspiratory hold, which is a maneuver that can help us locate where the issue is in the lungs. So when we think of vent types, we need to keep in mind that there are two kinds of breaths. Mandatory breaths that the machine carries out and spontaneous breaths that are patient-driven. And vent types are divided on just this. The vent can be all mandatory breaths, all spontaneous breaths, or both spontaneous and mandatory breaths. If we have all mandatory breaths, this is continuous mandatory ventilation, or CMV. Similarly, if we have all spontaneous breaths, this is continuous spontaneous ventilation. And if we have mandatory breaths that are intermittent, this is called synchronized intermittent mandatory ventilation, or SIMV. The word synchronized here means that both breaths are timed appropriately together. An example of CMV is assist control. An example of CSV is CPAP. And two types of SIMV are volume control and pressure control. And these are the ones that we are going to talk about. Let's start with volume control. So we have three graphs for volume, pressure, and flow rate, and we will look at one breath at both inspiration and expiration. In volume control, we have a set tidal volume that needs to be inhaled with every breath. It doesn't matter what pressure we have to get to. Notice that we start off with some pressure, which is PEEP, and we get to a peak inspiratory pressure, or PIP. Then we exhale, and flow rate is just the slope of the volume curve, so it's constant during inspiration. One of the major pros of volume control is that we have better control of PaCO2. If we look back to our minute ventilation equation, we see that with set tidal volumes that we are sure to reach at every breath, ventilation, which is expelling CO2, will also be well controlled. The cons of volume control are that because we must get a certain amount of tidal volume into the lungs with each breath, the PIPs can get dangerously high if there is low compliance or too much airway resistance, and high pressures can cause barotrauma. Switching over to pressure control, we set a pressure limit for every breath, and the volume of air then follows. Then expiration happens and we return to PEEP. Since the volume curve is sloped, flow rate will also be sloped. And this changing rate will actually be more comfortable for the patient than a flat rate. The pros of pressure control are that pressures are controlled, so this keeps alveoli open and it's more comfortable for the patient. The cons are that tidal volumes can vary. If volumes get too high, we can cause volutrauma, and if the volumes get too small, we can get hypoventilation and increased PaCO2 levels if we think about the minute ventilation equation. When we compare both machines, we see that in pressure control, pressure is constant, but in volume control, we are really controlling flow rate. I want to now zoom into the pressure curve of volume control SIMV to talk about a special maneuver. The inspiratory hold maneuver can help us locate where the disease is, in the airways, represented by the trachea and bronchi, or in the parenchyma, depicted by the alveoli. Let's see what happens to pressure in the airway during a breath. We start with baseline PEEP. At the start of inspiration, pressure must overcome the resistance of the airways, and then the vent must deliver enough pressure to inflate the alveoli. At the end of inspiration, we get a PIP, or peak inspiratory pressure, and the patient exhales and pressures return to baseline PEEP. As we can see, we can't differentiate which pressure is from the airway and how much is from the parenchyma. That's where the inspiratory hold comes in. It's literally a button on the vent and is equivalent to holding your breath after inhalation and measuring pressures. Let's see what happens. We start off the same. Inspiration starts when we give enough pressure to overcome airway resistance. Then we give enough pressure to inflate the alveoli so that we reach PIP. Now, at the end of inspiration, a valve closes and air can't exit or enter. Pressure goes down because we aren't pushing new air through the airways, and instead the pressure is concentrated in the alveoli and we get a plateau pressure, and this plateau pressure reflects alveolar pressure. The valve is then opened and pressure returns to PEEP. We will now look at two cases. In the first case, there is bad stuff in the parenchyma causing low compliance. Examples are pneumonia, atelectasis, pulmonary edema, pneumothorax. Because of the low compliance, we need more pressure to inflate the alveoli, and our PIPs will increase. Since plateau pressure reflects alveolar pressure, it will also be elevated. In the second case, there is an issue in the airways. This could be mucus plugging, a tubing obstruction like the patient biting the ET tube, or bronchospasm that we see in asthma. Since there is increased resistance in the airways, we expect higher PIPs. But since plateau pressure reflects alveolar pressure and our issue is in the airways, plateau pressure should stay the same. So to sum up, when we see increased PIPs, do an inspiratory hold maneuver, and we either get plateau pressures that are increased and reflect low lung or chest wall compliance, or normal plateau pressure, which indicates increased airway resistance.